Okay, so let's talk more about the in-depth structure of the binary heap. Okay, so we have a binary heap here because that it looks like a complete tree, right? It's filled in from the left to the right, and then heap property is right. This is bigger than 19 is bigger than 17, 17 is bigger than 2, 17 is bigger than 7, 3 is bigger than 1, and so forth. Okay, so it looks like it keeps the shape property and heap property, so this is a perfect binary heap. And let's erase a little bit. And to insert the next element, the only place it doesn't violate the complete tree constraint is these locations, right? This is the only place the next node can come in, right? So to insert the next node of the size 11, size 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, size 11, we need to navigate to this certain position of this place, indicating size 11. This is size 10 of the priority queue binary heap, size 9, size 8, and size 7 location. And how to navigate to the size 11? How can we identify how to navigate to the left, to the right, to the right? Actually, what happens all the time is that it's going to be order of log n, because this is the height, and it will take this height time of the iteration. So the navigation time itself is already fixed. However, how to navigate left, right, or left or right, determining that is a question. How to do that? Actually, it is pretty simple math that you have to think about for a while. I will just show you. So this is size 11, size 11. So what we are going to do is divide 11 by 2, and it's going to be 5, and remainder is going to be 1, and divide 2, and it divides into 2, and remainder is 1, and 2, and 1, and 0, right? And what we are going to do is take this, dump the first number, and we are going to take in this order. So it's going to be 0, 1, 1. Whenever we hit 0, it's going to be left. And whenever we hit right, it's going to be 1, and it's going to be right. So in this case, the first one is left iteration, left-hand side, and this next thing 1 indicates the right-hand side, and next one indicates the right-hand side. This is the perfect relation for the size 11th node, right? It's interesting. Let's do it one more time. Let's do it one more time. And my choice is, let's say, 6. 6. In this case, 6 and 2, 3, and 0, 2, 1, and 1. We dump the first value, and you take this value and this way. 1, 0, and 1 is right, and 0 is left. 1 is right, and 0 is left, right? And this is perfect place for this 6th node of this complete tree. And let's do it one more time. Let's do it. How about your choice is yes. Let's do it 7, 8, 9. 9th node. 9, 2, 4, 1, 2, 2, 0, and 2, 1, and 0. And we dump the first value, and we take these values and this way 0, 0, 1, and left, left, and right. Left, left, and right. Yes, this is the 9th node. why happens that? Why can we utilize this trick? Because we are dividing to the half of the size. And here is the repeating problem, the half of the size. Left, right is determined in that way. So, for example, so this ninth node is going to below the the first part of this tree, right? It's not going to be in the second part of this big tree, and it's going to be in the second part of this big tree, and it's going to be this part of this small tree. How can you determine that? Let's imagine that this is a size of 3 node. In that case, this is the first element, and this is second element, and this is the third element. If we divide 2 with this size values, this will have the 1, right? This will have the 0, and this will have the 1. And this is its own value is the dividend value is 1, and this is going to be 0, right? So this 0 indicates this is parent, and this 1 indicates is child, and its 0 is that it's next element, right? And this 1 indicates is a child, and this 1 indicates this is the next element of this node. So it's going to be right hand side. So by dividing it by 2, we can determine whether it should go to the left hand side or the right hand side. And if we expand this kind of approach to the upper level, we achieve the similar logic, right? We achieve the similar logic, and we can apply to the bigger ones as well. So the key point here is that we have to utilize the log of n operations to reach to this particular node. And actually, it takes a little bit of time. It's not like n order of n operations, but order of log n operation itself takes some time. Okay, so in the previous example, we talked about the implementation using reference. Here, we are going to utilize the array instead of the reference. Why we certainly utilize the array? So binary heap, utilizing the binary heap is trying to achieve the maximum efficiency of the priority queue. Having said that, to access to this last element in the reference-based implementations takes always log of n. However, in utilizing the array, if we have a right index, in the condition that we have a right correct index, you can access to order of 1 all the time in the array-based index. But to do that, we have to know the exact position of the array to insert a certain node. So this is the array, and this is the heap structure, and this array represents the heap structure. So you see this index, and you see this value here. By the index, if we annotate this thing, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. While we are annotating this, we can identify this kind of rule. If we set this as this certain node as an I, if this node's index as an I, then the left-hand side node is 2i, and the right-hand side node is actually 2i plus 1. And this is actually applicable to every node in this example. Why is that? Why we can do that? Because this tree grows by the factor of 2. By the factor of 2. So whenever we have a certain node as a parent, then it grows by the factor of 2. So we have to, in the next level, we have to multiply it by the 2. And by the 2 means that it's the left hand side. And the right hand side actually has to increase one more, so 2i plus 1 is included. So if we can write down this kind of characteristic, we have this ith node left child is 2i and ith node right child is 2i plus 1. And by utilizing these two properties to find out a parent, what we can do is actually we can just divide it by 2, and if we divide it by 2, it's going to be 2i, and it's going to be I plus 0.5, right? And this 0.5 doesn't make any sense in terms of the index. This is why this is happening. Why? Because that the node number increases by the factor of 2. So if we take this also bottom of this, then it will be okay. So what we are going to do to find out a certain node's parent is that we can just divide it by 2 and take the bottom of it. And finally, the node for the next insert is the tree size plus 1, and this it means that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Tree size 10 and plus 1 is 11th. 11th node is the next node to insert. That's here. So means that if we can just track the tree size, we can access to a certain node position up to here, right? And actually it should be index 11. Sorry about that. That's an error from the PPT.